My first task is to explain to you why we've been handing you little slips of colored paper. You should all have a slip of paper. Professor Hoffmann has generously decided to make available to some members of the audience, because we couldn't afford to supply all of you with copies of some of his works. So they're color-coded, and we have copies to distribute at the end of the event. No one will be asked to stand up and perform. Instead, you just need to turn in your colored slip, which is coded for the appropriate book. The colors are green, blue, lavender, and I'd like to call one of them coral, sort of red. Alas, if you have a yellow slip, you are out of luck. I think we probably should have put the URL for the appropriate Amazon.com site on there so you could order a copy. In a moment, I'll turn the podium over to Alan Rock, distinguished university professor here at Case Western Reserve and the Henry Eldridge Bourne Professor of History. He's been a member of the faculty here at CWRU for more than 35 years. He's a historian of science, specializing in the physical sciences and in particular in chemistry, the development of chemistry in the 19th century. In his teaching and in his research, he exemplifies the principles that the two sides of Euclid Avenue really reflect only one culture of which we are all participants. It's a great pleasure to be hosting this event in the Center for the Humanities. I'd like to ask Professor Rock to introduce our speaker this afternoon.
Thank you, Peter. It's a privilege and honor to introduce Professor Hoffmann this afternoon. But before I do, I just want to thank Peter and also Maggie Kaminsky of the Baker-Nord Center, who have made this event both financially and logistically possible. This event is an important part of ongoing efforts here at Case Western Reserve, as Peter mentioned, to foster productive interactions between the sciences and the humanities. More particularly, it is the culminating event of Baker-Nord Science and Humanities Thematic Seminar Group, which was not led by me, but rather by Chris Halfa in our philosophy department. And I want to give a big thanks to Chris for putting that together, for organizing it, for conducting it. It was a wonderful experience. Our speaker this afternoon is Dr. Roald Hoffmann, Professor of Chemistry and Frank Rhodes Professor of Humane Letters, Emeritus at Cornell University. It's hard to know just what to say about Roald Hoffmann, for once you start, you're not soon finished. And I don't want to take much time away from what he has to say today. But here are a few quick bio snippets. Born in Poland, 1937, survived the Nazi occupation when a righteous Ukrainian Gentile secretly sheltered him and his mother, came to the United States in 1949, studied at Columbia University, where he nearly decided to major in art history, but chose chemistry instead, earned his doctorate at Harvard with the eventual Nobelist William Lipscomb, hired at Cornell in 1965, where he made full professor at the age of 30, Nobel Prize in 1981 at the age of 43, National Medal of Science 2 years later, and a very long list of other major honors. I don't know why anybody hasn't made a movie about this man yet. Roald Hoffmann and co-authors have published around 600 scientific articles, and he has written or co-authored over a dozen books. His chemical specialty is how better to understand and to predict from quantum mechanical theoretical models the electronic structures of molecules and the course of chemical reactions. Roald describes this work using the apparent oxymoron, applied theoretical chemistry. I first encountered his name in 1970 as a graduate student in chemistry when I learned when I learned the Woodward-Hoffmann orbital symmetry rules. But for our particular purposes this afternoon, it is better to understand that Roald Hoffmann is also a highly successful and prolific and very fine playwright and poet and writer. It is fair to say that Roald Hoffmann is one of the most eminent specialists of the humanities of science, and he is surely the leading authority in this area called humanities of chemistry. He is also, I might say, a very fine human being. His title this afternoon is Chemistry and Art, Art in Chemistry, and the Spiritual Ground They Share. Professor Hoffmann.
Thank you, Alan. It's really nice to be here. Let me launch right into what I have to say. So first of all, chemistry and art. So here is our three masterworks of ancient art, a wall painting from Luxor in Thebes at left, in the center, the Gate of Ishtar, which once stood in Babylon, and then through a feat of imperialism for a change not American, found its way to Berlin, where you can see it today. And at right is a Hellenistic wall painting, actually from Egypt, a period, as you can see, of realistic representation that preceded the Italian Renaissance by a mere 1,500 years. Now, there is a green or a blue in all of these, and that's what I want to talk about. And a blue was always available. Green could be a pigment by itself, but in this case, it is a mixture of blue and yellow. And there was always a source of blue, which you see at lower left, as expensive then as it is today. And this is ultramarine. When Giotto painted the Scrovegni Chapel in Padua, he had the patrons to pay for that pigment. But the blue that is in all three of these is not ultramarine or powdered lapis lazuli. It is a product of chemistry done before there were ever chemists, a kind of proto-chemistry. It is Egyptian blue, essentially a side product of the Egyptian mastery of faience and of glass. It's a glass, basically, with a copper pigment of the turquoise or malachite kind that's in there. That's the chromophore. And we didn't know its structure till about 20 years ago, but that really doesn't matter. What matters is that people were making this and selling it, both of them, and making it reasonably reproducibly in these ancient times. So there was chemistry before chemists. Here's another story of which I have a whole lecture, but you will not hear it. It is about the pigment indigo and a variant of it with some bromines. Initially, the pigment was used in a Tyrian or royal purple, also written into the Bible in Numbers as a ritual pigment to be put in the fringes of religious Jews that they wore on an undergarment and in a probe of the high priest called the chelet. And this is a mixture of indigo and dibromo indigo, except it wasn't called that. And a product of mastery of these by the Phoenicians, traded around the Mediterranean. All the time there was a plant source from families of the pea family, Indigofera, which you see in the middle, and at right something in more temperate climates, a variant called Woad in English, Weid in German, Pastel in French, which are all sources of the indigo. The snail source was the only one which had some of the bromine pigment and brominated indigo. And eventually, 1877, we learn through that aspect of cultural evolution, which we call chemistry, eventually found its way to knowing the atomic structure of that Bayer in this particular pigment. The brominated compound is only found in a sea source. There is so much more to say about pigments. By and large, artists, especially oil painters, are a rather conservative bunch in terms of what they allow into their palette. And it is interesting what has penetrated, let's say, the palette of the oil painter. And on the blue side, there are a number of things. Ultramarine is now made synthetically and is generally available. Very interesting pigment from a chemical point of view. The very first well-manufactured pigment after Egyptian blue, which was not used by the painter so much, is Prussian blue, which has a very definite period of discovery and manufacture from the first decade of the 18th century, a very productive period in industrial chemistry and art, because that was also when Europeans in that decade were able to manufacture porcelain, to reproduce the ancient Chinese manufacture of porcelain. Blues and greens of a very intense kind and photostable, based on phthalocyanines, are now available. And the word is still out, I think, overall, on replacements for cadmium yellow, which people worry about because of health reasons. But there may be some pigments that are revealed that come in there. The other interaction of chemistry in art comes through an art form which depended initially entirely on chemistry. I show this because this is from an exhibition that unfortunately closed last month, and so I couldn't see it, unfortunately for me, though I hope that some of you saw it, about surrealism in photography. And this is one remarkable image from there, from the Cleveland Museum, of a crystal ball by Jacques-Henri Lartigue. So photography. Oh, it's so sad that most of the young people in the audience have not become familiarized with the smell and the manipulations of developing a photograph and printing it. Once you've done it, or once you've done it a few times, you never forget it. It's the entire ambience, the red light, the smell of the developer, the sloshing around in the water in the developer, and before your eyes, magically, the image swims out. There is just nothing like it. And that is part of what this shows, is the chemistry of photography. So what shall we do? It's not that we do away with chemistry, because instead of that developer and those things, there are now phosphors, liquid crystals, and OLEDs. It's just that you are distanced so much more, and no one is sloshing around in OLEDs. They are done in a factory in Korea and put on a screen there, and there you see it. But you don't have the practical experience of playing with these things. Let's talk a little bit about art in chemistry. This was the chemistry in art. There's much more to say, but it's not, we don't have the time for it. Here is a page from an article that I published at the end of 2012. And even though these images are produced by a computer program, what I want you to notice, and which is that how large a fraction of the page is taken up by images and not by curves which show the plotting. Well, I'm a theoretician. I'm talking here about the design of some hypothetical molecules, but I'm drawing them out. And actually, even though the drawings are done by a computer, there are artistic choices of various kinds made in these drawings. It's not just me, though in fact, my articles are recognizable by colleagues by the density of representation of molecular orbitals in them, which you didn't see in that previous slide. But here is from Helmut Schwarz, a leading German chemist. And again, you see the great multitude. Someone once asked me, write something about, this was for a program for writing across the curriculum. And someone asked me, write something about writing chemistry. And I said, I cannot do that. I can only write about writing and drawing chemistry, because the two are inevitably tied up with each other. And this is not just me now, but here there's a cover of one of Alan's great books. But from that book, there is a collage of people struggling in mid-19th century to represent somehow the connection of atoms to each other. But you see how they are in the variety of ways. Here are some actual physical models by another Hoffmann with one F, August Wilhelm Hoffmann. There are other ways in which people are struggling to represent the three-dimensional reality in models or on the two-dimensional things that are given to us. This is, I was very lucky I saved this. This is two sides of a napkin. The proverbial napkin, now not in your local Chinese restaurant, but if you look there, there is something which dates this, and that is where it was done. It was done at the Men's Faculty Club of Columbia University. That could not happen after about 1975, that there could be such a thing as a men's faculty club. But there it was, and I'm talking to my colleagues at Columbia after or in the course of a visit where I'm giving a seminar, and we're talking to each other, and there's no way we can talk to each other without drawing the molecules. So this shows you right away. Now, is this art? Well, that's an interesting story, and we'll get to pieces of it. Here's another part of the story, and that is that we have these three-dimensional objects, and in chemistry courses, we represent them in models, or they can be represented in a computer. But when we talk to each other, as I did in the course of the discussion over here, then I must represent these on a two-dimensional medium. Oh, yes, there will come a day when, like in the movie Matrix, you will be all walking around with a plug at the back of your head. And you will be plugged in, and through a virtual reality program, you will be able to feel the molecule. But we're not there quite yet, though virtual reality is about to penetrate the representation of molecules. But what we do, as you see at lower right, is we represent that molecule with a semiotics, which is taught in a second-year organic chemistry course in chemistry, by which you learn how to represent that three-dimensional structure, and the fact that it's a tetrahedron immediately throws you into 3 dimensions, that you learn to represent it by a code. Those wedges mean coming out in front, the dashed lines mean going in back of the screen. There's an interesting story here, which I mentioned at the top, and that is, here are chemists. They are forced to represent things in 3 dimensions. It's a matter of life and death sometimes, when there's the difference between a pharmaceutical and its mirror image. And yet, they are not talented at doing so. They are not selected for being chemists on the basis of their ability to draw. My ability to draw a human face atrophied at age 6. I did not get good instruction in representation. So what do we have here? Well, you have a situation, a bunch of people asked to do something that's impossible for them to do. That's one definition of life. And they learn how to do it. They invent a code, a semiotics, as I mentioned. But part of what is going on is extremely interesting psychologically, because that code is learned while manipulating a 3-dimensional model. And the link between tactility and representation is a very strong one. Once you learn how to draw this while holding the model and while twisting the model, manipulating it three-dimensionally, forever you will be able to reconstruct in the inside of your mind the three-dimensionality from the two-dimensional representation. And so what happens when we have now, as we do, 3 generations of chemists and biochemists who have seen the image of a protein on a computer screen and zoomed into it in Star Wars fashion, but still not felt an actual model of that protein. What has happened to their three-dimensional imagination? It's an interesting problem in psychology. But there is something here. Chemistry is, we're continuing to talk about art in chemistry. Chemistry is the art craft business, that was those pigments, Egyptian pigments, and now science of substances and their transformations. I didn't know if the safety committee of this hall would allow me to do an experiment to demonstrate this, so I show you these 3 images, 2 substances which were just about for the first time discovered in their pure form 200 years ago, aluminum and bromine, and one is placed into the other, and you get flames, foul odors, smoke, absolutely everything you expected of chemistry. And at the end is something totally different. This was chemistry, this is chemistry. If you want to read about how the smells, stinks, and colors attracted young people to chemistry as they do today, you could read it, for instance, in Oliver Sacks' memoir, Uncle Tungsten, told very well. Now, these transformations are inherent. Here's some drawings by R.B. Woodward, a great organic chemist, in the course of some discussion, again, with somebody. One thing that I want you to notice, that how is this transformation, the changing aspect? We saw how the structure of the molecule is represented badly or well, but now how about the transformation? So there's a code. Part of that code is simply the arrow that you see here. And he's showing that there are some transformations happening. Of course, the arrow plays a large part in the art of a very interesting artist, Paul Klee. The picture at upper left is in a museum a few hundred meters from here. I couldn't resist the one at right, which has an important arrow in it because of it's called Hoffmanneske Geschichte, a Hoffmannian story. This is after another Hoffmann, too. The arrows are there as representation. Paul Klee has a whole philosophy of art developed on arrows and forces. Here I want to tell you just a tiny snippet of another story which makes a little point about art. There's another lecture about the commonalities between art and science, and part of what you are exploring in your seminars. And there are also differences. And one of the differences between art and science that's usually talked about is in terms that science deals with universals, but art deals with particulars. And there is a density of symbols also, and the kind of symbols, iconic or symbolic, that are in them that could be talked about. One difference is, you might think, and I'm going to just show you an example from this, that in pointing against it, might be that, you solve a problem in science, it's solved. But a million poems have been written about the end of love. It's okay to write the 1,001st poem, and you will write it, some of you. because that's not a problem that's capable of a solution. So now let's go, let's take off a little from that, but before I get to that, I want to show you this molecule. It's Taxol. It's become part of an anti-tumor regime, a molecule which was initially isolated from the bark of a Pacific yew tree. And you can get about 3 doses of the drug from the bark of a whole tree, and you kill the tree, which took 300 years to grow. This is not going to be a way to make a drug, even with all the precedent that Merck, Sharp, and Dome has for extracting money from the government's pockets or our pockets. You can't do this, and so there's a structure of the molecule in 2 models. Interesting that you need 2 representative. Why? If there is a unique solution and unique resolution, why do you need 2 ways to show it? Or 3 ways. I've seen a video called 30 Views of an Enzyme, recalling the 30 Views of Fuji, Hokusai's suite of etchings. It's an interesting story there. The Taxol has to be, if it's going to be a drug that's going to be useful, let's not worry about the costs at the moment, it'll either have to be made synthetically, it has been, or it needs to be made from some semi-synthetically, from some molecule which has most of the terrible complexity that is before your eyes in this molecule. And so, in fact, it is made that way, semi-synthetically, in the doses that are used in chemotherapy. It's made from the bark and leaves, rather, of another yew tree, an ornamental yew tree that can be farmed and doesn't take 300 years to grow. But what I want to show you is a page. I'm not going to go into the details, but it's from a synthesis of Taxol by my friend Sam Danishevsky, and there is a lot of art in building up the molecule. These arrows are what is called a retrosynthetic analysis. It is the way that the molecule that you want to make, which is the top left, Taxol, the way it is thought up to be constructed, and the real construction will go in the reverse direction, of course, from simplicity to complexity, starting from molecule 1 and winding up with Taxol at the end. And each of these steps actually may be a multitude of steps. What I want to show you is simply the fact that the 3rd synthesis of Taxol, not the 1st and not the 2nd, but the 3rd synthesis of this molecule is publishable in the best scientific journal in the world. So there is something about how could it be published? It would not be publishable if it were identical to the 1st synthesis. It's different. Is it better? That's an interesting question. What does better mean? Is it less expensive? Does it take fewer steps? It turns out that there are all kinds of aesthetic, chemical, but aesthetic criteria still, stylistic criteria in the synthesis, the surprises along the way it was planned that no one else had planned it that way, that can be applied to the creation of the same object at the end that was done by somebody else before, and everyone in a community accepts it. In fact, if you open the Wikipedia article on Taxol, you will find 7 syntheses and 7 pages, different pages with the different syntheses, and there are more. But let's talk about the most interesting thing, which is the spiritual ground. And I'll try to clarify what I mean by that. It's a loaded word for some. the spiritual ground that chemistry and art share. And incidentally, as you've seen, when I've used the word art, I've generally referred here to what in German is called die bildende Künste, that is the visual arts, the representational arts. But in that is something I will fight to in a moment. So it's about transformation. So that's interesting, because an interesting cultural phenomenon and a particular interaction of chemistry and philosophy is that when there arose across cultures in India, in China, in Egypt, in Greece, at roughly contemporaneous times, and the linkages are interesting, when there arose philosophies of transformation that needed, that were inherently hermetic, secretive in some way, and complicated. And when those philosophies of transformation, well, first of all, what kind of transformation? On the face of it, simply human desired transformation, which means sick to healthy, poor to wealthy, perhaps longing for immortality. A number of Chinese emperors died under the influence of some of the things that they were fed in that search for immortality. But also psychologically transformation in other ways. I'm talking about alchemy, as you can see from these representations. When there arose these philosophies of transformation, and they needed a symbol or a logo or something to get into people's minds with, because they were complicated, they chose, I believe, something which already to people, even though they didn't have, those people didn't have aluminum and bromine, something which to people, even in ancient times, represented the essence of transformation, which is A plus B giving C that's different from A plus B. And that is chemistry. And that was chemistry. Now, this is not your normal view of alchemy. The normal view of alchemy is it's a pseudoscience, so people, so chemists scoff at it. It was a precursor of chemistry. They also, they don't bother reading some of the underlying philosophy, and they not chuckle a little nervously at the charlatanry that inevitably accompanied something like the transformation of lead into gold. Here's a typical alchemical illustration. You see the strangeness of this enterprise. Michael Mayer's illustration from a compendium of 3 alchemical texts that he edited. I mean, in the back is a king and a queen getting married by a bishop or a cardinal, and in front is some chemistry. Now, it was given to me in the 60s to go to a number of hippie weddings in California, and I saw some chemistry done at those, but it wasn't this kind of chemistry. Okay, so what you see here, obviously what's going on in front in these recognizably chemical things, the vessels that we see to this day as traces, is some sort of transformation which stands for, is symbolic for the marriage that is taking place in the back, another kind of transformation that is happening. One is a symbol for the other. There is a relation here to a remarkable genre of the emblem books of the Renaissance in these representations, another story. The alchemy is to me, and first of all, alchemy lends itself to illustrations. Mayer's are not the only ones. and the emblem books are full of alchemical things happening. To me, alchemy is, among other things, is a mixture of chemistry and art coming in conjunction, culture. Yeah, here is a product of Cleveland culture, which I was hoping to taste because I come from the part of the world where these were made. But they're going to treat me to much more fancy things, I fear, than this, or corned beef. But this also is transformation. So what's the transformation that's going on here in forming pierogi and the sour cream too? First of all, there is this incredible transformation from the nitrogen of the atmosphere to the fertilizer, and that fertilizer eventually to ammonia, and then going on to wheat that is in the pierogi dough, and then going on to you and me at the bottom. Now, there's a whole sequence of transformations in there. These transformations involve all kinds of fascinating chemistry. For instance, you might not know that the nodules in the roots of leguminous plants contain an enzyme called nitrogenase that allows the bacteria in those nodules to accomplish something which we, the pinnacle of evolution, cannot do, which is to turn nitrogen into ammonia. We breathe in the nitrogen and we breathe it right out, 80% of the atmosphere. And it causes no trouble, nor does it serve us in any way. It causes trouble for divers, but that's another story. But for us, it does nothing. And we are dependent ultimately on a bacteria to fix the nitrogen. And of all things, it involves an enzyme, which is the crucial site of the enzyme, has a cluster of 7 iron atoms and 1 molybdenum. I mean, who would have thought up this thing, molybdenum, in living things? And then on the other side, we have the Haber-Bosch process. And there is just an emblematic factory, but underneath, much too small, is the sequence of steps which from Gerhard Ertel's work we have learned happens in that transformation. It's a magic thing. So here is Mircea Eliade saying something from a wonderful book, which in English is called The Forge and the Crucible. I've forgotten what in the original French it was. But what he says is, I'll transcribe it. What he says is modern chemists screaming to high heaven that they have nothing to do with alchemists have accomplished everything the alchemists set out to do. And what he means is, what he's talking about is Merck, Sharp, and Dome. The dirt is the starting materials of their synthesis. The gold is what we pay them. And real healing takes place along the way. It's actually a very interesting time to have accomplished the alchemist's dream. Okay, I want to talk about something a little more difficult, and this is to ask a question which is still within the subject of the spiritual ground we share, but now I want to ask a difficult question, and that is, for instance, it's easy the easy questions of chemistry and representational art are easy. But let's talk about abstraction. So abstraction looks about as artistic a concept as you can have. And what I want to ask is there such a thing possible as abstract science? Or is there abstraction in chemistry? In what way? So here I'll show you that I think there is in a certain way. What you see at left here is a sculpture by a Cornell faculty member, Roberto Bertoia, the son of another sculptor. And on the right, you see a molecule of 3 intertwined rings made by Fraser Stoddard. here are two great works of abstraction. Actually, your museum has a Rothko, and it has an Elizabeth Murray. I think it's called Keyhole. It's right on the wall. I saw it this morning, but I like this one a little bit better. But it's in very much the same series as the one that's in the Cleveland Museum. These are typical superb works of abstraction. So what is abstraction about? Before we can talk about abstract science, we have to talk about abstraction in art. So abstraction defined itself initially in terms of an opposition to something. And the opposition was the natural. And the actual definition took place in Russia. So that's why I show you one of the great Russian landscapes, one of the great landscapes ever painted by Isaac Levitan, not so well known in the United States as it should be, but it's clearly a representational work. We're now in the second half of the 19th century, and he's painting it this way. Now, here are two abstract work of art. It's not so easy to define abstraction. I'm reaching back in the past. I've taken both here from down the street, and what you see at left is a Japanese work of art, a bowl which is a vase, a container, which is a mere 4,500 years old. This is the Jomon ware. That is quite remarkable. And at right, you see a tunic from the Wari culture. I'm not going to say the word to describe the period. Let's call it Andean art. I don't want to define it by the colonialist term that we use. These are remarkable control of design and of the dyeing of the pigments in these, we are fortunate to have these preserved. We are usually familiar with the Inca culture. The Inca had a short run of it, of about 100 years before the Spanish did them in. But before the Inca, there was a number of cultures in a rough area of Peru and reaching up north to Colombia and south to Chile, which are the Wari, one of them, Moche, is another one, and the Nazca cultures. And you can see the Cleveland Museum has an extraordinarily good collection of these works of art. But back to Russia. At a little bit after Levitan paints that landscape, we see the defining exposition of abstract art. This is Kazimir Malevich in a room. This is actually a photograph. You can have photography. We actually see the art exhibition at the so-called suprematist exhibition during World War I. And in this, he paints a black on black. And he also defines his terms. And he says, as you can see here, you can read it as well as I, about a manifesto. It's going to be typically aggressive. Only a cowardly consciousness and meager creative powers and an artist are deceived by this fraud and base their art on the forms of nature. Afraid of losing the foundation on which the savage and the academy based their art. And to reproduce beloved objects in little corners of nature, that's Levitan, is just like a thief being enraptured by his leg in irons. Okay, he's going to go on like this. So, very quickly, even without thinking, he realizes that to define yourself, this is just like against abortion or pro-life. Defining yourself by negativity is not the way to go. Or that you must create a raison d'etre for your existence, and he's doing it right away. The square is the creation of intuitive reason. It is the face of the new art. It is a living royal infant. The revolution hasn't come yet. It's 2 years to come. It is the first step of pure creation in art. Ah, pure. Now, so this is how the abstraction philosophy justifies itself. That is, it's not only against nature, but it is the pure art by concentrating on the basic elements of artistic creation, which might be form, color, something like that. Now, there is a little bit of problem. The word pure doesn't matter whether it's used by Malevich or whether it's used by the Nazis, is going to get you into deep, dark trouble eventually. And I am inherently suspicious of anything that has the word pure. That's because I know as a chemist that the aroma of a good Cabernet Sauvignon contains 900 chemicals. And you're going to fake it by one chemical? Nothing in nature. The only thing that's pure in our world is that which comes from the very best chemical laboratories, and it's not very pure. Anything natural, for reasons, for good evolutionary reasons, is as impure as need be in order to go on with the business of propagating. So what can chemistry be against? Let's take the against aspect. Of course, the same damn thing, the natural. So the natural is represented here by hemoglobin, what's in red blood cells. How boring to, after you figured out what hemoglobin is, to try to make a molecule that is like hemoglobin, no matter how difficult it is to do. Why not make things which have no chance of natural existence? Molecules which are shaped like platonic solids, for instance. Or actually, Buckminster fullerene, the molecule at lower right that deserves to be on a flag of Brazil, the molecule which is actually been found, even though it was made synthetically, but it has been found also in nature. Here is about as unnatural, or an interesting thing, unnatural, combination of natural and unnatural. Ned Seaman at NYU, this is a schematic, but every one of those chains is a chain of DNA. And he has coerced, dictated the DNA to curl up into the shape of a cube, which no self-respecting DNA molecule would want to do. And this is about as, well, it's interesting. It's a natural molecule coerced to do something, well, not that different from what Malevich did. He's using paints and pigments in order to illustrate this, so to make his square. But here is another kind of unnatural thing. So normal amino acids are ones which are called alpha amino acids. You see it at the top. There is an NH2, and that's the amino group, the COOH, the acid group. In the middle is a CH2, and one of those hydrogens can be replaced by 19 other groups to make the common 20 amino acids. And then they are strung together into a protein to assemble the analog of a Swiss Army knife, but infinitely complicated to do all the chemical function that you want to do. So here is Alana Shepherds at Yale, and what she's doing is making beta amino acids. Why? Well, what she'll tell the granting agency is she is doing it in order to possibly make some things which are close to alpha amino acids, but which might then fool some bacterial enzyme or a apparatus to incorporate it, and then later on it would not have the function of a normal amino acid. But the real reason she's doing it is just for fun, okay? So this is, it's amusing to try to manipulate reality. Is something here akin to what Ned Seaman is doing, in order to explore what changing that reality does. Very much a kind of playing of a game with it. So let me go to this other aspect of abstraction. And this is an intense concentration in abstraction on something or other, on formal relationships, on the outside of the frame to the center, on color, on geometric shapes, on curves of one type or another, on optical illusions. There are a number of them running through abstraction. Here is one of my favorite abstract artists, Ad Reinhardt. The Cleveland Museum has only one, which is not in display, which is a black-on-black painting of his. Here are some of the more colorful ones. You can see what he is doing, and you could see the continuity of this. These are from around 1950 to 1960. Here is Roberto Bertoia, the sculptor whose work I mentioned. And what he is exploring here, again, you can see the concentration. That every one of these shapes that you see is different, but you can see what he's playing with. He's playing with the aspects of enclosure, of space, of containing space, of space coming out. There are little windows here. And of us moving in that space in different ways. It's all rectangular, but these are not natural objects, yet they have a certain relationship to natural objects, we'll see. So what is the chemistry analog? So one of the things chemists do, you remember that synthesis of Taxol, which I sped by? That synthesis of Taxol involved building complexity from simplicity. If I took apart every step of it, I would find that many of the steps involved the formation of new CC bonds. A rather pedestrian enterprise. And in fact, one of the first such ways is something called a Wurtz reaction, which is at upper right, where an R, which stands for some organic group, an X for a halogen, is reacted with metallic sodium, and out you get a linkage of the two R's to each other with a new carbon-carbon bond formed in the process. This is obviously away from simplicity to complexity, which is the general direction of chemical synthesis. So when you go to Wikipedia, there are 102 pages on carbon-carbon forming reactions. And if you think that's all, the organic chemists on your faculty, when the 102 ways to do this, when that a poor graduate student has tried to effect it, when they fail, you can be sure that the professor will direct them to a paper with the 103rd way to do this. So this is a concentrate, and there are many very good chemists who concentrate on something like forming a bond and forming it reproducibly under different conditions. I already mentioned it. Let's talk about something else which is obviously associated with abstraction. And this is, in part, it is the macho image of Jackson Pollock here, using his muscle, getting his exercise instead of going to the gym by throwing paint at the canvas. It looks like chance is what is at work here, but actually, as a number of people have pointed out, if you look at Jackson Pollock paintings, there is a lot more than just chance. There is chance at work, but he does things near the, and he doesn't paint, there are some painters who do this, but he doesn't paint 100 square meters and then cut it up into pieces. Because what he does near the frames, near the edges of his painting, is very interesting and very well designed in its way. Chance comes up in art in other ways. This is a Japanese ceramic, now 4,500 years after Jomon. This is Japanese studio ceramics. This is Bizen, a certain town in Japan with a certain way of firing, a certain clay, and Jun Isazaki, a great potter. The shape was designed by him. It was placed then in a kiln, and the kiln was filled with some leaves and other things to produce a degree of shielding and, to a chemist, oxidation or reduction in the process of firing it. But I can assure you that he did not design to get this pattern. But I can also assure you, because I've watched this process, that he was strong enough to throw away 9 out of the 10 things that came out of that kiln because they were not sufficiently, they did not have the chance working in the way that he could perceive would produce an artistic product. So what is the analog in chemistry for a role for chance? There is something called combinatorial chemistry, which was very fashionable about 10 years ago, is now a little down, but the general idea is not bad because nature uses it in part of the process. And that is that if you want to design a molecule to fit a certain site, you see, for instance, the yellow, red, and blue, and green fitting in a certain site in a target molecule. So what you're doing here is designing a drug to fit a certain bacterial DNA molecule that is different from a human DNA molecule, let us say. So what you do is you just throw in the building blocks and you find some chemistry, dynamic combinatorial chemistry, which combines the building blocks not by design but by chance into every possible combination of 1, 2, 3, and 4, but you better not ask for 17 because this chain explodes very quickly, combinatorially. And then you find the target, you let the target pick whatever binds to it, but then you have a way of analyzing it so that you find out what it is that has been bound to, and then you make that reproducibly. So this is a clever way of using combinatorial. Let's talk a little. I haven't talked much about music, and I really don't have the ability to talk about this, but music is very interesting. It's the most abstract art form we have. Now, when I say this, I exclude tone poems and other things of that type, and I'm missing a Stravinsky quotation, which enables me to exclude those. He says something, this is Igor Stravinsky, that at the heart of all good creation in music lies an appetite for things not of this world. Now, in part, that's an artistic statement, but it is something in there. A Haydn trio, which is incredibly beautiful, is nevertheless a sequence of tones with a certain time sequence. So the most important thing probably in music, aside from the pitch, is the timing of the sequence of the sounds. And that aspect is there in chemistry as well. I show you another synthesis. I don't have the time to go through this in detail, but it happens to be the first synthesis of penicillin during World War II in 1943. When I was in Poland and I had German measles, I could have benefited from this, but I didn't, and I had to struggle through this as a child in other ways. Sheehan assembles the complexity. Let's see if I can, if you can see. No, you can't. I have to enable my arrow, and I haven't learned how to do this. He assembles the complexity, and at the end of it, maybe you see in a penicillin 5 molecule, there's a 4-membered ring with a nitrogen and a CO at lower left of the molecule. That's the hard part of assembling it. And he does it by, at the right time, throwing in a reagent, which I've circled, not circled, put in a rectangle in red, called DCC, Someone has a pointer. And then that molecule goes in, and that molecule plucks out of that. Notice all the arrows flying around there also. An interesting bit of notation. It plucks out the elements of water. And at lower left in the synthesis, you see the same molecule, but now added to it is an oxygen and two hydrogens that have been plucked out of water. Plucked out of the molecule, and a ring formed at the same time. You know, that molecule thrown into that reaction mixture at any point other than the point it was thrown in would do nothing except create black gunk, the most usual product of a chemical synthesis. And so the timing is very important. Now, I come toward the end with a problem. And this is a problem that abstraction and conceptual art also, which I haven't talked about, that abstraction has in common with science and with chemistry in particular. And that is a problem of emotional impact. That is, it's cool. And abstraction, now here are two examples. There's a Frank Stella painting close to those Elizabeth Murray ones coming out of the wall. This one at lower right by Julian Stanchek is one playing with colors, actually quite organic, and with wave shapes. This one is from the Cleveland Museum also. And at upper right, you see a nitrogen atom inside a fullerene molecule, and at lower left, you see my favorite Taxol again. The problem with these things is that I can justify the problematic of abstraction in both abstract art, but you know it's just talk and problematic. And it's stuff for Ph.D. theses and for art historians and for chemists. But what feeling do you get on contemplating these objects? So it is clear that any human representation is going to engender an emotion that's immediate. It may be positive, it may be negative. You get a different representation to a Renaissance Madonna than you get to Goya's etchings of war. But you get an immediate reaction, and you get that even in the absence of human beings in that Leviton landscape that I showed you. And these things are relatively cool. But what can we do about that? I think Mark Rothko didn't think what he was doing was cool. And I want to show you a room. This is the Rothko Chapel in Houston. And it is covered wall to wall, every aspect of the chapel, with abstract black on black paintings. And here is another image from it. Now, I have been in that chapel, and I have seen people cry in that chapel. And that is exactly what Rothko wanted to do. He wrote about this. The act of contemplation, the disinterested act of contemplation, if you give yourself a chance and let your mind float into the object and then reflect from that object on you. And I think you can do it with chemistry too, though you have to be privy to the cognitive structure of chemistry, and we have a harder road on this. But I think it can have an emotional impact. I tell you, the people, the good organic chemists I know, on seeing the Danishevsky synthesis, have a very special feeling about it. At Reinhardt, when he was asked about this, much more reasoned than Kazimir Malevich, said, "Some claim to represent nature, hell on earth, sick society, inner turmoil, wild beasts and things as they are. May not one side of me speak up for the angels, for the side of the angels?" And underneath is a verse in the original German from Rainer Maria Rilke, that every angel is terrifying, and yet, alas, I invoke you, almost deadly birds of the soul, knowing about you. I feel there is an emotional range in this, and I feel that there is a spiritual ground that we share, and I'm glad to have told you about it. Thank you.
Thank you very much, Roald. Wonderful talk. Roald will be happy to answer some questions. Maybe I should do this here. And afterwards, sign a few books. If you have questions for Roald, we invite you to come up. This is being recorded, so we ask that you come up, and whoever wants to ask a question can line up at the microphone right here in front. Don't be shy.
Does anyone know from where in American literature I copied this strategy for giving out the books? Well, I copied it from Carl Gerasi, who died recently and who did this, but it's the Tom Sawyer strategy. If you go back to Mark Twain's and the scene about Tom Sawyer scheming to get a Bible, even though he didn't go to church classes, you will see some of the same strategy. I'll be glad to answer any questions, and if anyone has, please come up and ask.
Hi. Thank you for a great talk. My question relates to one of the last things you said, that when chemists see a certain reaction, that it touches them in a certain way. Is there any scientific role that feeling plays, right? That is, does it play a special cognitive role in the process of inquiry? Thank you.
I think what we see in the development of interests of chemists and the directions of young chemists, we see initially that interest in stinks, bangs, and colors. Okay, that's the first thing. But when that passes, it switches to a cognitive level of some sort. I don't mean to intellectualize it too much, but then it switches back to an emotional level, and it does it what I would call through a kind of virtue theory. What I mean by that is that you admire, you do what you do by emulating the virtue of the masters, so that you admire. You first see these books, classics in organic synthesis, or in a course, very often in a course, people set out some wonderful syntheses by the masters. That Sheehan synthesis of penicillin is one of those. There are syntheses by Woodward and by E.J. Corey, another great master of organic synthesis. And somehow these syntheses are little intellectual pieces of virtue which serve as models for young people to what they do. So this, for what they want to do and what they actually do. They model themselves on the masters. I think this doesn't look like this is science, but that's how it works.
My question is about ambiguity.
Yes.
When you were showing pictures of chemical structures, the need was for clarity and lack of ambiguity. But in artistic expression, sometimes it's unambiguous, an
Yes.
ode to autumn or something,
Yes.
perhaps. But in many cases, there is a deliberate ambiguity there, which is not quite a lack of clarity, but
Yes.
something related to it. I wonder if you could comment on that.
Yeah, so you've pointed out one of the other differences. I'm not going to do the analysis of the Rilke poem, but it's obvious that poetry works off ambiguity often, or at least positive ambiguity. That is, that in science, until you looked at those gleaming brass steam engines in Britain at the time of the Industrial Revolution, and they couldn't understand how they could never get the efficiency of those steam engines past a certain point, and they wouldn't understand it until the science of thermodynamics, thermochemistry was put into place with rigorous definitions of heat, work, and energy, and then we could understand. Whereas in writing a poem, that a word means several things, and that it sounds like three other words that mean something totally different, is the stuff of which poetry is made. So that is one of the differences, aside from this, between science and art. I don't want to talk too much about the differences, but I should tell you about the similarities, commonalities, rather. Another difference, aside from ambiguity, is universality versus specificity. So that E equals mc squared work for every mass is the essence of that particular law. And it does work whether it's nuclear reactors or atomic bombs. Whereas the poem works through something, even though he's talking about angels generally, there is a specific angel we image. And my friend and guru Archie Ammons, when he would talk about, he would portray a blade of grass, it is that specific blade of grass and the universality for all. Then he would say, I would look at this weed and it has a drop of dew which has an image of me looking at it in it. That was a particular drop of weed, a particular drop of dew, and the universe was in it. And that is the wonder of good poetry or good art. So those are differences. However, now the next thing I'm going to say gets me into trouble. I think chemistry among the sciences is, as in many ways, I'm prejudiced, but it's close to poetry, or I'm in a context of self-justification. It's many of the formative concepts of chemistry are not well defined and are ambiguous, in fact. And they become productive in suggesting new chemistry, by a curious mixture of precision and ambiguity. For the chemists in the audience, what I'm thinking of are ideas like functional group, acid, base, aromaticity. All of these things, when you try to define them carefully, wilt at the edges of the definition. And some people just cannot take it. Primo Levi was mentioned before. Primo Levi, at some point in his book, goes through this at age 20. He's got a crisis. He's been studying analytical chemistry in Torino, and he says all of a sudden it hit him, where are the theorems of chemistry? So he thinks he's going to find them over in the physics department. And he goes over and studies with an astrophysicist. And of course he finds, once you delve deeply into physics, you find it is as ambiguous, except I've done it, as ambiguous at the edges as some of those chemical concepts. It's just better hidden. And I think that freedom at the edges of the concept allows chemistry actually to go forward. So I think ambiguity is there in the science as well. This is not a fiat for the social construction of science here. I'm just dealing with the realities as I perceive them in my field.
If there are no more questions, maybe we can do this on a more informal way. You all have those slips, so you can redeem them for the appropriate book on your way out. If you'd like to have the book signed by Professor Hoffmann, then we can continue that conversation as a book signing. Okay, thank you all for coming tonight.